So today's video is about the IB electron configuration. The first thing we're going to do is a little recap. So before we get into this, I think the most important part is to kind of forget what you learned in GCSE, because this is a completely different way of electron configuration. But some of the things you might want to know is like nuclear charge. So that's the number of protons in a nucleus. Something new we learned is electron shielding. That's the fact that the greater number of shells, the more the force of the nucleus is shielded from the valence electrons. You'll also need to know atomic number, atomic mass as well. So the first thing we're going to look at is the configuration of an atom. So if you'll have the shells, which are the main energy levels. You'll have the subshells. Under the subshells, you have orbitals, and then finally you have the electrons themselves. So the number of electrons per main energy level is given by 2n squared, where n is the shell number from the nucleus. So if this is the nucleus, this will be shell number 1, this will be shell number 2, and this will be shell number 3. So if we put that into the formula, the first shell will only have 2 electrons. The second can have 8, 2 times 2 to the power of 2. So the next thing we need to figure out is the sublevel classification and the orbitals. So if we go back here, we see that after the shells, we have subshells, and then we have orbitals. You can also call this sublevels. Okay, so for the sublevels, they're classified by, these are the 4 notations we need to know: S, P, D, F. We'll mostly be working with S, P, and D. So these are basically because each sublevel has varying energies, and these notations depict that. You then have your orbitals. So each orbital depicts the orbiting of an actual probability of an electron density. So basically what this means is you have the nucleus, and around the nucleus you have orbits of electron densities, and these orbits are known as orbitals, and they are denoted by px, py, and pz. These are the 3 things you need to know. There will be another video on orbital shapes, but it will give you a better understanding of what we mean by orbitals. So this is the full overview of the electron configuration. So you have these. You basically just need to know the 4 main shells. Under shell number 1, you'll have the subshell S. Under 2, SP. Under 3, SPD, and under 4, SPDF. So you only need to know till there. Under the main first main sublevel, you will have under the first shell, you will have 1 orbital. Under the second, you have 1 and 3. Under the third, you have 1, 3, 5. And then under the fourth, you have 1, 3, 5, 7. So it's pretty easy to remember. And then if we look at the max number of electrons, in the first orbital, you will only have 2 electrons. In the second, you can have 8. The third, you have 18. And the fourth, you have 32. And we call this the octet rule. So if you ever forget, go back to the formula, 2n squared. So now let's look at orbital diagrams and energy level diagrams. These help us understand the configuration and how to write it out. This is very important. So here, this is the nucleus. Just picture that as the nucleus. And what you want to do is you want to write down all your orbitals. So 1s2, 2s2, 2p6, 3s2, 3p6. Just write them out from left to right. And if we look at this, so here you have the orbital. Here you have the subshell, and this exponent shows you how many electrons can be in that orbital. So 1s2 means there's only 2 electrons there. 2s2, 2 electrons, but it's in the second subshell. 2p6, it's the p orbital. You have 6 electrons, and it's in the second subshell. So that's how we write it out. And then once you've written out in this format, so left to right, and you just keep writing it out, you want to draw arrows going horizontally through each, okay? And what that helps us do is figure out the order in which we write this out when writing out the electron configuration. I'll talk more about why 4s2 is before 3d10, and so on. So one rule you always want to remember is that you always add electrons to the 4s orbital first, and also take away from the 4s orbital. So next we have the energy level diagram. So you can see this is the nucleus. This is energy increasing. So you have 1s, 2s 2p, 3s 3p, 4s 4p 3d. So you can see 4s is at a lower energy level than 3d. And then 5s is at a lower energy level than 4d. So that's very important to remember. And you can also see here the varying energy levels of the different orbitals, as I mentioned before. So there are two rules that you need to remember. The first one is the, whoops, sorry. Stop that again. So there are two rules that you need to remember. The first one is the Aufbau principle. So basically the principle states that you must fill electrons from lower energy levels first to higher energy levels last. So this is where our orbital diagram comes in, because if we follow the orbital diagram, it will order our orbitals from low energy to high energy. And we see that 4s comes before 3d. It's because when the 4s the 4s orbital is empty, it is at a lower energy level than 3d. But when electrons are added into the 4s level, it becomes a higher energy level than 3d, which is why we take away from 4s first, but we also add to 4s first. The next principle we need to know is the Pauli exclusion principle. This basically states that each orbital holds a maximum of 2 electrons with an opposite spin. Now this is something new. An opposite spin, we basically write our electrons, so this is one electron and this is another electron. The reason we write opposite spin and we write our electrons like this is because of repulsion. So when the two electrons are together, they will repulse each other, and this is why we denote it like that. So the Pauli exclusion principle states that you always fill in the electrons like this first, and then go in with the opposite spin. This is because atoms would rather have an incomplete orbital than an empty one. There are exceptions, of course. So now we're going to try writing it out. If we look at lithium, it has an atomic number of 3. So go back to your orbital diagram, and we'll see that we start with 1s2, and that's taking care of 2 electrons, so we only have 1 left. And then we write 2s1, and that's all 3 electrons taken care of. Now we go to carbon. So again, carbon's atomic number is 6, so we write 1s2, 2s2, so that's 4 electrons, 2p2, and that's 6. Then we go to argon. Argon has an atomic number of 18, so we go 1s2, 2s2, that's 4, 2p6, that's 10, 3s2, that's 12, 3p6, that's 18, and we'll notice that this is completely filled up. It is a stable noble gas. Coming on to noble gases, we actually use noble gases as a shorthand to prevent us from writing everything out each time, especially when we go further into the periodic table. It would be very futile to write everything out. So so helium, you basically write helium like this, and then you continue on the electronic configuration after helium. And same with argon, and the same with neon. That's it. Thank you.